Yeah, let's now talk about PyTorch custom data loader. So the data loader is a class in PyTorch that lets us load data more conveniently compared to doing it manually. I will show you two notebooks. One is just the data loader itself with a simple example, and then I will show you how we can use it in a model training context. So, what I should say is I'm actually using MNIST here, and you may wonder why MNIST, because there's already MNIST dataset and data loader implemented in Torch Vision, which we could technically import, which is what we have done in the last couple of videos. So the reason is MNIST is relatively small, and in this way I can upload it to GitHub, so I can upload this without, let's say, taking too much space in that repository, and it's also for you faster to download. And it was just convenient because you are already familiar with it. But of course here MNIST represents a more general dataset, so think of it as an arbitrary dataset consisting of PNG files. So what I've done is I divided MNIST into three parts: a training set, a validation set, and a test set. So I put them here into PNG files. Just in each folder there's a set of PNG files, as you can see here. And I have also a corresponding CSV file. So here in the CSV file I have the class labels and the file name. Of course, you can also, if you like, you can have only one folder with PNG files and then have a column with validation, train, and test index. So you can also specify it like this. I mean, how you set it up is up to you. I sometimes find it convenient to do it like this. Sometimes I only have one gigantic PNG file folder and keep track of what is training, what is validation, what is test. I keep track of it with columns in the CSV file. But this is really optional. I mean, like, how you want to set up is up to you. You can set it up however you like, and I will show you how we can then handle that with PyTorch dataset class. So back to this notebook. So I showed you now I have these files. So focus now only on these three folders and these CSV files. The helper function, I will use them later in this train model notebook. Let's get started. So usually when I have a new data set, what I do first is I inspect this data set. So I sometimes use image.io, sometimes I just use the Python image library. I'm not very consistent. It doesn't really matter. There are multiple libraries in Python that let you open a PNG file or JPEG file in Python itself, and then you can take a look at it. So here I'm using PIL, that's the Python imaging library. If you have to install it, I think you have to do conda install pillow. Why pillow and not why PIL or PIL? That is because the Python imaging library, I think it got abandoned at some point, and then some people forked it on GitHub to further maintain it, and this fork is called Pillow. But even if you install it as Pillow, the import is identical. You use this one to import it. And here in particular we are only importing this image class. So here I'm just looking at the image. So here I'm loading one data point or one image from this MNIST train folder. Why CMap binary? Because the color maps by default is this Viridis color map, which is kind of useful for heat maps, but here maybe it looks a bit goofy if we have these colors for MNIST, so here we use just this version. Alright, also I find it helpful to just take a look at the image dimensions. So here it's 28 by 28, there is no color channel, and you can see the values, the pixel values are between 0 and 255. It could be 254, I'm not quite sure. Here actually I see the highest one is 253. Alright, so then looks okay, so we know what we are working with. Let's now load the CSV files. Loading pandas, and then I'm loading my CSV files. So these are only the first 5 rows with this head command. And I can also show you, you can see it right here. the data set is, only I made it artificially small. There are only 256 images in each data set. MNIST is of course much bigger. It's usually, I think 50,000 in the training set and 10,000 in a test set. Here I just made it smaller because I'm going to upload this to GitHub, so you can download it, and in this way, it's not like taking up too much space there. Otherwise, I don't want to upload 50,000 small files and stuff, All right, so here, here's our interesting part now. That's the dataset class in PyTorch, and so in order to use the data loader, we need a data set. So there are two parts. One is the data set and one is the data loader. So let's talk about the data set first, because that's what we need for making the data loader. So here the data set is really how we read the data. So this is something you have to set up yourself for a new data set. So here, this is from PyTorch, Torch Utils Data. This is a class from PyTorch, and here this is called class inheritance in Python. So we are inheriting certain features from dataset so that they are available in our dataset. So it's called class inheritance. It's like not a PyTorch but a Python concept. So, and then we're defining our own dataset. I'm just calling it my dataset, but you can call it whatever you like. And then, like in every class, we have an init method, and here in this constructor, in this init method, I'm specifying certain things. It's basically, by the way, arbitrary what I put here. It's not required to put anything here, but what we need here, because we have CSV files and we have folders, I put both the CSV path, the path to the CSV file, let's say the training CSV, and the image directory, for example here this directory. And there's also a transform for doing a custom image transformation. I will show you just a very basic transformation. Actually, we're not doing any transformation. I will talk about this in the next lecture. So what's going on here is in the init. In the init, we are loading the CSV file and keep it attached to the data loader. We don't need it attached. One second. So we load the CSV file. We save the image directory to the self.imageder attribute so we can use it later. And then we save the image names as self.image names. And this comes from the CSV file, from the file name column. So if I scroll up again, this is this column. We just save this column here. And then we also save the class label column as self.y. These are our class labels. And then we just store whatever we provide as transform here. So this is a setup for the dataset when it's created. And here, this is how a data point gets loaded, a single data point. Remember that this one was showed you in the animation, loading a pair of, or a data point with its training label, basically. So one image and one label. So that's what what's loaded with this get item here. Here, you have to have this index here. I mean, there are other ways, but I find it convenient with the index. And then we have to specify. So what we do is here we specify how we obtain one image and one corresponding label. So how do we open the image? So image.open. So this is similar to what I used up here. Image.open. And then I'm giving it the path. So the path is based on the image directory that I provide here, and then the image name. So the image name is in this column, right? So here what img is, it will be, for example, something like MNIST train, let's say 1.png. So here index will select a random one, so it could be either 1 or 3 or 5 or 1 to 123, whatever. So this is chosen randomly. So this is how this data set is basically shuffled, by always picking the indices in random order. And then there is an optional transformation that we can apply to the images. For example, normalization, rotation, and things like that. And I will show you how that works in the next lecture. So, and then we also obtain the corresponding class label. So if index is, let's say, 1, then we will, or let's say index is here 1, then we would obtain image 513.png and the corresponding label 0. And then it returns both the image and the label. And that's essentially it. There's one more method here, that's the len, and this one is the length of the data set. So that is how this data set knows when one epoch is finished. So here we can simply compute the length by getting the shape of this y, which is the class label column. So essentially I have not imported anything here. I actually should have. Df is not defined, huh? Oh, I called it df train. All right. Okay. So this is our data set. So this is really specifying how we load a data set or images from the data set. And now this is the data loader that is also loading data points, but this is really for making our mini batches. So for doing that, we need the data set. So here what I'm doing is I'm setting up the training data set. So the training data set has the CSV file mnist_train.csv and the folder mnist_train. This is this folder here and this CSV file. Let me, before I explain this in more detail, also show you the validation data set. So here's the same thing for the validation set, but notice that the folder names are different and the CSV file names are different. And here is the same for the test set. Now, see, there's another thing going on, transform, and this is our custom transformation. We don't do anything here except converting the image to a PyTorch tensor. So there's the Torch Vision library, which has this transforms package or sub-library, and there are different methods for augmenting and transforming images. Here I'm using something called toTensor, and this one will convert an image to a PyTorch tensor, but it will also normalize the images by dividing them by 255 automatically. I actually find this, I don't know, I would like if it wouldn't do this automatically, because it's maybe something we don't want to do, but in any case, it does that. So what I mean is, it would be cool to have the choice whether we do it or not. Maybe there's a new function that has or gives you the choice, but it's actually not a bad idea to normalize images. So in that way, it's maybe good so people avoid making mistakes, because training a network on unnormalized images is usually a bad idea. Okay, so this is how we then set up our training dataset. Now we have created a dataset, a training dataset, using our myDataset class that we defined here. So here, this is just defining the class, and here we are actually using it. And now we are setting up the data loader. So that's the main part, which takes in this training dataset. And here we also specify the batch size. We specify whether we shuffle or not after each epoch. So this is shuffling or essentially before each epoch. And there is also a parameter num workers. So it would be great to have a whiteboard here or something. I don't have one, but think about it as this. So if Python is single threaded usually, so there's one main Python process, one process running. So there's usually, let's say, data processing, and then there's our model, and this, let's say, we give our data to the GPU, and then on the GPU there happens the model training, and then it goes back to data processing again, and then it's basically a repeating loop. So we're going from data processing to the GPU, where we do the model training, and then data processing, GPU, model training. And this would also be true for CPU. The main point is that this is sequential, because Python is usually one single process, one main process. However, data processing can be slow. I mean, it can take, let's say, 10 seconds or 5 seconds to load the images. So it would be more efficient if we have the data processing decoupled from giving the data to the GPU and the model training, if those happen like in parallel, right? So we could have actually multiple CPUs. Via multiple CPUs, we can do the data processing, and then the data is already ready in the memory, and the GPU just has to read it and do the model training. And it has never has to wait until the next batch is processed. So in that sense, we can use multi-processing of our CPU to prepare the next batch of images for the GPU, so the GPU doesn't have to wait. For that, we can use the number of workers greater than 0. If we have 0, then only one main Python process is used for both, for everything, for the whole pipeline. If we set it to 1, then it will create one sub-process to load the data, which is makes it more efficient, and 2 is even better. I noticed when I run it here, actually I get problems recently with recent versions. I think this is because MNIST is so fast to load that it will just load too many things at once, and then it has too many open files waiting for the GPU to be processed. So I get nowadays an error when I run it on MNIST. But if I have any other data set other than MNIST, that is usually not a problem, because MNIST is really just too simple. I think that's the problem. So I set it to 0, but in your projects, you may want to set it to a higher number. For example, in my research projects, I usually use 2 or 3 without problems. Yeah. Oh, I should also explain what drop last means. So if you have a number that is, let's say, not divisible by 32, then there will be a last batch that is smaller than 32, right? And if drop last is true, it will be dropped. You don't have to do this. I mean, like, you don't have to drop this, but I noticed sometimes in my research code that if I have, let's say, batch sizes of 512, and then the last batch has only 11 examples, this last batch can be extremely noisy and sometimes harm the model performance. It does a bad update at the end of the epoch. So personally, in my projects, I found usually dropping the last mini batch, if it's smaller than the batch size, is sometimes good. All right, let's take a look now. So here we are initializing all the data loaders for the training set, for the validation set, and the test set. And here I'm just, I'm iterating through it to just make sure that it works. So here I'm simulating how we would train a model. So we have, let's say, just 2 epochs, and then we iterate through the batches here. For our training loader, this is actually what you have seen before. We have used the built-in MNIST dataset. Here I'm transferring it to the device. So the device, if you have a GPU, it will be the first GPU. Otherwise, it will be the CPU. So it will just iterate. See? So it just gives a batch size. So it will create 1, 2, 3, 4, 5, 6, 7, 8 mini batches. And that is it. Let me change this to 1 and see what happens. So I don't always get this error, but with MNIST, see, I get something called like this. I think this is because there are too many open files. It doesn't say so explicitly, because the weird thing is I don't get this error when I run this on data sets that are not MNIST. There's something about MNIST. I think MNIST is just too simple. It's a little bit weird, to be honest. Also, I can't remember in the past getting this error, but anyways. Could also be my computer, because I compiled PyTorch from scratch, but I also get this error on my other machine, so anyways. So let's go back to this one. And here we can also just print the shape of one of the batches here. So the shape is 32. Then the color channel is only one color channel, so because it's black and white. And then 28 pixels high, 28 pixels wide. Here's just printing it as a vector. If we reshape it, 32 times 784. So this is what our multilayer perceptron needs as an input. So convolutional networks can work with this input directly. Multilayer perceptrons cannot, they can only work with this. And this just for reference how it looks like, the torch tensor. You can see it's normalized. We should be able, maybe we can't. Let's just see if it, because it's abbreviating it. Let's see if we can print it. Here you can see the highest value is 0.999 because it's 253 divided by 255. All right, so this is how the data loader works. Let me now show you the model training code here using the custom data loader. So here I'm now using a hybrid of what I showed you 2 videos ago when I use helper functions, helper scripts and a Jupyter Notebook. So here I've set up several helper files that I may reuse in different projects. And this helps me keeping the notebook kind of small. So if I make a new notebook, let's say I call it notebook 2, I can make some changes to this notebook, for example, some settings, but I don't have to copy and paste all the code. It's in that way easier to read, especially if you want to, let's say, modify some function. There's a bug in the accuracy function, then you don't have to go back to every file here and change the code. You only have to change it in one of the files in the Py files. So I can just maybe open them, show you what I mean. So, for example, helper evaluate, I have this set all seeds, deterministic, compute accuracy. So if there's a bug, for example, I only have to change it here once. I don't have to go back to all my notebooks. I find this very helpful if I have a project with multiple model training and model notebook scripts, or notebooks and scripts. All right, let me close this again. We can take a look at individual ones. So here I'm importing certain functions from this. From these helper files. Then here are my settings. You can also, like I explained before, have a separate settings file. Here I have it just in the notebook itself. Random seed, batch size, and number of epochs. And then I'm using these to make that deterministic. And here is just, so here I have a get data loaders function that actually uses the data loader from the previous notebook that I showed you. I just put it into this script here. Now I have my data set here. And I have written a get data loader, which will set it up for me automatically. So that's basically just a slightly modified version of what I've showed you in the previous notebook, where I just have arbitrary paths and stuff. And then it will return the training loader, validation loader, and test loader. And here I'm just testing that they actually work. So just getting some statistics. And you can see, so if I run this again, you can see that the shuffling works because you can see that these numbers change. So these are the first 10 labels. So you can see, so every time it will start from scratch because I break here. So you can see these numbers change. However, if I set my random seed, I always get the same order. See, I can run this again. Always get the same order because of the random seed. The random seed, makes the makes it consistent. It's so, for example, if you run this code, you will get the same model and same accuracy I got because you use the same random seed. This is useful, for example, if you do research and you develop some code and want to share it with someone else and the other person wants to reproduce your code. So here is the multilayer perceptron. I simplified this a little bit. So I'm using sequential now. I mean simplified compared to 2 videos ago. Here I'm actually using flatten. This is actually new. I like this a lot. So this way we don't have to reshape our feature vector. So it will essentially reshape the 28 by 28 to 784 for us. So we don't have to do it manually somewhere down here. And this is it. So here I'm using sequential, so I don't have to do anything in the forward. It will automatically return the logits. So here this is a multi-layer perceptron with only one hidden layer. So this is the first hidden layer. Then we have the sigmoid activation, and then we have the output layer. And then we would technically have a softmax, but we don't need to have the softmax because the functional cross-entropy loss in PyTorch computes the softmax for us. Alright, so this is how it works. So don't need to set another seed here because I've done that above. So here the seed would be for the initial random weights. We'll also talk about this in 2 lectures. So not the next lecture, but the lecture after that, we will talk about these different ways we can initialize weights. We use stochastic gradient descent. And here I also just brought a function for training the model. It's essentially what you've seen before. I just put it into a separate file here. So if I go to helper.train.py, I have all the code I had previously in here. Because it's essentially always the same code, so you can use that in other projects as well. You can just copy and paste it. It just keeps the notebook more readable in that way. It's not such a long notebook anymore. Oops, what do we got here? Yep, that's what I always forget, defining things. All right, so it trains. It will train very fast actually, because we only have 256 data points in each data set. Yep, it is training fast. Yeah, we get actually pretty high accuracy. I mean, given that we only have 256 images, it's also barely overfitting. It's actually not even, you can see it's 91% and 73%. It is overfitting. But yeah, the validation accuracy and test accuracy are almost identical. The difference here, why is the difference? It's usually just a small random effect, right? Because it's a small data set, 256. And then I also have functions for plotting the training loss and the accuracy. It's also helpful. So I have the version with a running average. And you can see the loss goes down. We are trained for 100 epochs. And here the accuracy goes up, but then at some point, there's more and more overfitting. So I put these plotting functions in helper.plotting if you ever need them. I think I will also personally reuse them in future lectures, because then I don't have to make these long notebooks, because this code is really always the same. So I have it sometime defined here, and then I can reuse that. You don't have to honestly memorize any of that, or it's good maybe to understand it if you want to change it, but you don't even technically have to understand any of these details. So it's also something I wrote one time, and if I ever need it again, I'll just copy and paste it. Because there are too many other things to worry about. It's rewriting this it took me some time. There were some bugs and things didn't work, and that way you write it once so that it works, and then you can just reuse it. All right, so last, as a show examples function I wrote, so it shows some of the images, so you can see P means predicted and T means true label or target label. So these are all correct. So here this is predicted as 2, but the target is 6. I think I made an error here. That can't be right. Maybe it is right, but let me double check. I haven't planned this. It's very spontaneous, so good that we look at it. I think it's, sorry, it's my mistake. No, I just wrote this code actually for this lecture, so made a mistake. Okay, let's do this again. Oops, should have been targets. One disadvantage is because I have the import at the top of this notebook. I have to run the whole notebook. But it's fast to run. All right, so that looks better now. Predicted 6, target 2, predicted 5, well, target 0. Some other mistake here. You can see the model makes some mistakes, but I think these are just mistakes because the model hasn't seen enough numbers, because these should be easy to distinguish. I think they are clearly number 2s. Okay, so this is the custom data loader. So that's it then for this lecture. Next week we will talk about regularization, like preventing overfitting. All right, have a good weekend.